Good evening, everyone. We'll be getting started in just a minute. All right, let's begin. So this week, we're going to have a look at how anti-cheat works for Windows games, as well as taking a brief look at how cheating actually happens. Some of the stuff here will probably kind of coincide with our Mac OS game hawking talk we had quite a ways back, but it should be a nice review either way, even if you've seen that before. So let's begin with one of the best forms of cheating possible, the famous word.exe. Now this cheat system is impossible to stop. It is top of the line, and so we're not going to talk. Everyone knows this stuff's too powerful. But what about the rest of us that don't have word.exe installed on a computer at a competitive CSGO event? What do we have to deal with instead? Well, so anti-cheat is a lot like antivirus. In both situations, we're trying to find out if something malicious is happening. And we're operating on a system that we don't control necessarily. Antivirus, unfortunately, has to deal with the user. And anti-cheat has to deal with the fact that it's not running on a machine that the developer owns. It's your computer. Well, maybe it isn't if you're playing Valorant, but we'll get to that. So game engines are quite complicated. There's a lot going on in them, and that makes them interesting both from a reverse engineering perspective and from a cheating perspective. But first, let's just have a look at some of the underlying Windows concepts that we need to understand what comes next. So the most important thing for us in this whole talk here is the concept of a handle. A handle is like a pointer, kind of like a file descriptor. It references things on your system. It could be, a whole process. It could be a single module, that kind of thing. And in the user land, they can be a little bit opaque. We have to keep track of exactly what it's supposed to be. Well, the kernel, on the other hand, has all that data written down, so it knows exactly what it's dealing with. And we have this excellent metaphor here. It's just like you're at 65,535 deli counters. You take a ticket at 934 of them. You get an arbitrary number, and the deli knows what it means, but you have to keep track of it yourself. And in this situation, we're also trying to steal all of the ham. So, since we're looking at evasion, we're going to assume, this is kind of the base level, that we have privileged access on the machine. So, if all you have is a no permissions account, you're not going to be doing much here. But because a cheater typically owns their own computer, a citation needed, they will have privileged access to it. They can run things as an administrator, for example, which gives them access to all kinds of things that are useful for debugging and otherwise kind of interacting with other processes. A nice smorgasbord here. We have, suspend thread, read process memory, write process memory. Those all sound quite useful. So assuming we have the privileges for these, we can do pretty much anything we want to anything on the system. I'm not going to read this entire list off step by step here, but if we want to, poke at something's memory, we can just ask Windows, give me all the programs, kind of scroll through those processes, see if we find the one we're looking for, Half-Life or, I don't know, Counter-Strike. Well, it's Global Offensive, I don't know what they call it, whatever that's called, and pop open, process. And by getting a handle to this process, we can then do things to it. For example, going to read process memory, we give it a handle, we give it an offset, it reads memory. And so we can just kind of browse around and close things out when we're finished. So here's our high-tech victim program for this little example. All this thing does, it has a little struct with a value and a function pointer that prints out the value. And all it does is just say, okay, add 10 and print it. It's pretty straightforward. If we look in Cheat Engine, we will indeed see that the value is going up over time. So if we get a handle to this process and then say, find out where its base position is, offset it appropriately to find where that struct is, we can just put a 0 there. And it starts counting from 10 because it increments before it prints. So you can see with relatively little effort, we can reach into another program and mess with it. All we have to do is figure out what is it named, okay, where is its module, and where in there is the data actually stored. So we kind of do a lot here. This kind of gives us what we might call external cheats, where you just poke at the data in the game from the outside. So if you're using Cheat Engine to get infinite missiles in Ace Combat 7, for example, that is kind of external cheating. You just kind of walk around memory until you find the number you want, or you just poke it. But what if we want more control? Like, if I was making an aimbot, I'd have to read my location. I'd have to get other people's locations. I have to do all these calculations. I got to write them back, and I don't want to do that again. I just want to have the game do it for me. So what we want to do here is get code running in the context of the process. So that means we aren't having some external thing reaching in and poking at it. No, we're actually going to put our own code in there. Now, as you can imagine, that might be a little easier for the anti-cheat to notice, but we can get onto that a little later. So we can actually take advantage of what's already in the program and just do things for us. So we're going to make it load an extra library and run its contents to hijack our beautiful little program. And again, just kind of putting this in short, we make some room for a library. We get the module in there, and we start to spawn a new remote thread, which will, upon coming to life, load the library and execute it. And we get we can make Notepad start spewing stuff at us, or we can, for example, upon injection, overwrite the function pointer, this guy here, and then just give it our own little function. And if we check up here, what it does, it just modifies the data a little, set it to 0, and then calls the original function. So we kind of pulled out some bits from the program and then just replaced its guts with our own function, which will do a little extra work. In this case, once we do the injection, it will just set the value to 0 every time, thus making it print 10 forever. So at this point, we can kind of do whatever we want. So we're no longer sitting outside looking in and jabbing at bits of memory with a stick. We've actually broken into the program here and started just running our own code. And so that means that at this point, we kind of have almost as much control as the developers would. We can insert entire functions, we can patch things, we can kind of swap stuff around. We can do whatever we want. So in the context of game hacking, we could do things like, okay, adjust my orientation to this angle, give me a list of all players, get me the locations, that kind of thing. And rather than having to exhaustively trudge through memory, we just do it for us. Now, outside of the context of games, there's also some interesting stuff here, because this is kind of the whole, not the whole premise, but a decent chunk of the premise of things like fuzzing and program analysis, especially dynamic instrumentation of programs. I believe we talked about that a little bit in the fall. So what we're doing in both cases here is inserting our own logic into the program to either help us get those sick aces in Counter-Strike, or to help us understand which functions are getting called and in what order. So, two sides of the same coin here. So a really common way to abuse this is to hook into DirectX So, DirectX is the graphics library that actually renders program. I mean, there's Vulkan too, but DirectX is, I think the first one you think of. You kind of think of a graphics library. So, suppose we were to, hook into draw index primitive, and when we're drawing a model with the exactly correct vertex count, just turn off the z-buffer test. For those unfamiliar, the z-buffer is the depth buffer. It says what renders in front of what. And if we just totally ignore that thing, we have wall hacks. Suddenly, the enemy players are rendering in front of everything else. So this gives us really simple wall hacks. You don't have to do any crazy logic to, draw your own models. You just kind of reach in, adjust a few things, and now you're a pro gamer. Congratulations. Unfortunately, games and gamers generally don't like hackers. You can imagine if every time you join a lobby, you get a person mic spamming and spinning in circles or instantly headshotting you from across the map, you're going to quit the game. You won't tell your friends to play it. Everyone is unhappy, except the hacker, I suppose. And even the hackers are going to get sad at some point. There's no one left to own. So we need to kind of find a way to detect this stuff. Now, how we do that is a little complicated. We need to play, kind of one thing we have to play with in the rules of, antivirus, for example. It can get a little bit pissy if we start doing really weird stuff as countermeasures. But we also have to be careful with what we're doing to the computer in general, So, different anti-cheat systems will have different goals. So, it's like, what are we trying to protect against? Are we protecting against Joe Random Cheater who just went on to mycheats.biz, paid $50 for Aimbot, and is trying to get some, cheap aces in Counter-Strike? Or are we trying to go after people developing cheats and shut them down and really make it possible to abuse the game? And these require vastly different amounts of effort. So, for today, we're going to have a look at Valve Anti-Cheat, beautifully rendered on the left, BattleEye, and Easy Anti-Cheat, as well as PunkBuster. So, PunkBuster is a classic anti-cheat system. I unfondly remember getting randomly kicked from games in Battlefield 21 and 42 by it. And it's pretty primitive. So, it does require super user access. And what it mostly does is it just kind of scans through your memory looking for signatures and cheats. If they've seen that some cheat has this string in it, they will include that string in the database. They see that string, they kick you. And it does some other less relevant stuff, like checking file integrity and taking screenshots of your system without your permission. It can be some surprisingly invasive stuff, showing all your configuration files to admins and so forth. So it does scan all of your memory, including memory that has nothing to do with, the running game. And this led to a pretty hilarious exploit where if you just found a string that would set off PunkBuster, you could just send it to people. Just toss them a message. Hey, here, just over IRC or I don't know if Skype. I guess Skype existed back then. Xfire. I think that's what I'm feeling more like right now. And that would lead to just people getting kicked en masse. I found an article claiming that they got over 300 people kicked, pretty much all at once from games just by spamming stuff at a large IRC server. So, a little bit coarse-grained, we would say. It also scans for very specific signatures. There's no heuristics here. So if it looks for, my cool cheat.exe, and then you just adjust that string so it's my, lame cheat.exe, doesn't find it. And now, the cycle will repeat. Once they find the exploit and they get the new signature, they will detect you again, but then you'll just change it again. And they did some more advanced stuff too, like trying to detect tampering and actually banning you based on hardware signatures, that kind of thing. But it was still a little simple. And it still exists too, kind of. I had a peek at their website. It looks like they last posted an update over a year ago, and the last update before that was from 2015. It also has an RSS feed, which I thought was quaint. So that's PunkBuster, but I think probably the most famous anti-cheat system around is, of course, VAC, or Valve Anti-Cheat. So this came around in about 2001 when they decided to stop using PunkBuster. Amusingly, I think that was shortly after they started using PunkBuster. And they claimed that they were kind of going for a more long-term anti-cheat solution. So this is a user mode anti-cheat. And remember that user mode means it's running at the same kind of level of privilege as you are, or as an administrator. So operating on ring 3, as they call it, rather than ring 0 in the kernel. And VAC's main goal is to deal with the Joe random hacker, somebody who's just buying a cheat off the internet and just ruining some games with it before getting banned. So it does signature scans. It will look kind of like PunkBuster. It looks for very specific things, and also it does have some other fun little tricks. vtable scanning DNS cache, that kind of thing. Looking for interesting behavior, but it's still mostly signature based. And it does a lot of the same things that our cheats do, actually. So what it'll do is, especially during startup, like the first few minutes of running, it will snapshot your processes and iterate through all of them, have a look at them with, get process information, and scan the processes that have handles open to the game. And incidentally, this is why I got banned from Warframe for a few days, because I left Cheat Engine open in the background. It was somewhat humiliating. I was trying to recover data from a crashed Overleaf session. It didn't work. I did get unbanned. So VAC also scans for libraries in memory and opens whatever the file location is and scans those as well. Amusingly, you could actually just change the file name to throw it off the trail. It would look for the incorrect name and just give up. So there's basically no heuristics here. It is like making sure that the game's code sections are correct and haven't been tampered with, but it's really not bulletproof or necessarily bullet resistant. So if you write your own private hack, because you're certain that you are, you deserve that high competitive rank. It's just all those you have table teammates, so you need to write your own hack to get good. It's just a little It's just a little wall hack. What's the big deal? So that little thing of yours probably won't wind up in the database because no one will hear about it. VAC can't really find novel systems. It just looks for stuff that Valve knows about. And you can do other weird things, like you inject into one process, then inject into the game. That VAC's going to scan the wrong process. It won't even look at you. If you just kind of reach in and poke your DLL memory directly instead of calling load library, you won't have some of the interesting headers that VAC will look for. And actually, we'll be talking about some of those pretty soon, so stay tuned for that. You can also just kind of pop your DLL out of the module list, kind of like how rootkits can just pop themselves out of a process list, and then the kind of standard kernel system calls they won't see it. So really, ultimately, VAC is not meant to target the elite cheat writer. It's designed to attack Joe Random cheater. Now, Valve does have an interesting idea that they kind of came up with a year or two ago. Of course, AI. Vacnet tries to detect the malicious behavior rather than malicious code. So it's not really relevant for us today, but it is an interesting little side. It's very effective at detecting people who turn on their spin bot and then just get, 50 kills in a row. It's much less effective against subtle cheaters, just like how humans are much worse at detecting that someone's using wall hacks rather than just instantly clicking on everyone's head. So back to VAC, though. So yeah, as we said, it lets you do pretty much whatever you want as long as you aren't, just using something off the shelf. And you can do some evasion too to really just shut it down. And as a result, there's no real reason to go into the kernel, unlike other anti-cheats we'll be looking at later. But you can. So there's a little thing on GitHub here, kernel-bhop or kernel-bunnyhop. it uses a driver to do the reads and writes. So your user space program talks to the driver, and the driver then pokes at memory. WinAPA never sees this, so Rack similarly never sees this. And this is a lot like a rootkit. We've brought this up a few times, just kind of talk about this here. So rootkits conceal themselves, at least one way they conceal themselves, is by doing direct kernel object manipulation, or DCOM, great name. So they can, for example, take the list of processes and just kind of unlink themselves. Or they can just kind of look for other processes and mess with them. Maybe stop Windows Defender from starting, or, just otherwise interfering with the system. So, it kind of has control of reality here. So antivirus can try to counter this. Like, it can scan memory for weird-looking kind of hidden processes, but it's difficult because the antivirus is not in control of the situation. And AntiCheat is in a similar situation here because, in this case, they don't own the system, and they generally can't be certain that what they're seeing is accurate. So that's kind of a general problem here, and it's one that attempts to be solved by the kernel-mode anti-cheats. So these are things like BattleEye and easy anti-cheat. So these things are a lot more aggressive. They will hook things all over the place. They constantly scan processes. They jam dynamically downloaded bytecode into processes. At first glance, you would probably say they're a rootkit, but in fact, they're anti-cheat. I think that's kind of potato there. Potato tomato, maybe. I don't know. But yeah, so in the kernel, there's a lot more to do. There's a lot more functions to mess around with, a lot more stuff to do. And then finally, these things are also heavily obfuscated. We talked about obfuscation, I think, last spring, and we'll probably bring that up again this semester. We did it in the fall. I think we did it in the fall. I have to go back and look. But yes, obfuscation allows you to make a lot harder to reverse engineer a program, doing things like rearranging functions, breaking things in little pieces, all the way up to making little virtual machines to run your code. So they really do not want you to understand these things. So the BattleEye, for example, will get a callback for when you create a handle. And what they'll do is knock permissions off the handles that are being created so that you just cannot interact with the game at all. Now, to get around this, there's a couple ways to deal with it. We could write our own driver. So basically, we're countering their kernel level thing with our kernel level thing to just put the permissions back on. Maybe doing it after little bits. They don't notice. We could actually just do that kind of bhop thing and just DIY the memory access. Or we could just try to find a way to trick Windows into giving us what we want. Now, to bypass the kernel mode anti-cheat stuff in user mode typically involves some kind of oversight in the kernel mode anti-cheat, because we cannot override what it wants. Like, we don't, it's in the kernel, we are not in the kernel, it wins. But there can be caveats and kind of these exceptions that we can abuse. So, for example, Windows has a few processes that if you Google the name, the first autocomplete is probably virus, because they actually are popular names for viruses, but also because people are a bit dumb. But so things like LSAS and RSS, these are Windows processes, and LSAS, for example, it kind of handles security management. So these things need a lot of access to programs in your computer. And if you try to mess with them too much, the computer just dies. So yeah, LSAS, it's, does networking, and more broadly, it deals with, security. So it kind of, creates tokens, enforces things, all that stuff. So they, BattleEye and easy anti-cheat can't just screw with its handles, because they will just destroy the computer, not destroy the computer, but they will cause a crash. So what they do instead is they attempt to check the integrity of LSAS. Looking at new executable regions, like, I wonder what that is, seeing if there's unusual threads running, see who's poking at LSAS, that kind of thing. So we're operating in a bit of a weird spot here, and you have to be careful when you're operating here, because if something is weird is going on in here, it's basically incontrovertible that you're cheating. With PunkBuster, it's a little bit easier to say, well, someone just sent me a funny message on Xfire. Here, it's I was putting some extra stuff in this process. So yeah, you have to be careful. So luckily for us, LSAS does have a few threads that are suspended after you boot. So like there's one here that after like 10 minutes, it just kind of turns itself off. So what we can do instead is just preemptively turn it off and take control of the thing. Now, you don't want to do this for just any thread, because there are plenty of threads that if you just kind of get rid of them, that your computer will get rid of itself with a beautiful blue screen. This one, though, is pretty safe. So we're going to hijack this thread. Now, unfortunately, anti-cheats are aware of this, so they're going to actually check what the thread's doing, too. If this one thread is executing a different module entirely, something's probably wrong. So what we can do is go all the way back to our classic, Honing 101 shell coding. And you might know that on basically any remotely modern system, you cannot just execute stuff off the stack. That doesn't work. But if we have, super user privileges here, we can indeed just say, okay, make this a read, write, execute page. And we're going to just do what we call code caving, which is finding some space that no one really needs and kind of putting our stuff in there. And this comes up a lot in malware and kind of evasion of antivirus and all that good stuff. Hollowing out processes, putting weird things in them, that kind of thing. So we have 3 kilobytes of space for shellcode. This gets kind of disgusting, though. We're doing a lot of very weird stuff. We're kind of just taking some C++ and just kind of compiling it and jamming it into a program where it shouldn't be and running. So yeah, it's not exactly ideal, and it can take a lot. You can wind up losing a lot of space to all the finagling all the different bits of the syscalls and actually getting access to what you want. But it is doable. So once we have this code in there, we can actually map some shared memory into LSAS and then just spin lock on it. And so a spin lock just says, just keep while true until something changes. And so what we could do is have another process kind of just go open that memory and just write some addresses, say, hey, read this for me. And it'll toggle the spin lock. So the shellcode then says, okay, I'm going to read that address for you. It's going to write the contents out and then just hand control back. So now we have inserted into LSAS this little bit of code that will allow us to read whatever memory you want. And importantly, LSAS cannot be denied access to things, because that can crash the computer. So that means that the anti-cheat just has to begrudgingly allow it, and thus we've gained access. So anti-cheats, if all they find is some weird stuff in memory, they're not going to. They're going to have some trouble banning you for that. If they're detecting more than that, then things get messy. But if we're keeping it to pretty minimal stuff, like just sticking minimal stuff at the end of a program, that in itself is a lot harder to detect and a lot harder to ban someone for. So it's pretty reliable. Now, for more recent events, some of you may have heard of Valorant and its Vanguard AntiCheat system from Riot Games. So this thing is even more aggressive. It starts on boot, and if you ever interrupt it, it will refuse to let you run the game until you've completely rebooted. So the objective here is to kind of get almost a secure boot-like thing where it's trying to maintain integrity of the system from power on, in perpetuity. So, for example, it will detect if you're trying to virtualize it and just refuse to work. This can also mean if you have any virtual box like DLLs lying around, it can just freak out and blow up. It also will, for example, refuse to work with any unsigned drivers, which means that you can't just write your own funny driver code and throw it in. You need, at the very least, have a way to sign your code and sign it in a way that it will trust. So, suddenly you're looking at having to get, I don't know what the exact certificate process is, but you have to go ask Microsoft very nicely, and then they'll probably say no. So this makes things a lot more annoying. So this sounds like two things simultaneously. One, a really overprotective antivirus, and two, a rootkit. And this has provoked large amounts of gamer outrage on the internet. So it's certainly interesting, and there's arguments. I've seen Riot arguing that if they wanted to steal all your data, they'd just do it anyway in user mode. While you might retort that by saying, "Well, I'm not letting you just hijack my entire computer here." Of course, cheaters have found ways around it almost immediately, which is pretty funny. But it is still reasonably effective, And so there's this sliding scale of kind of like really aggressive anti-cheat on one side, where it's one step away from them coming into him with a gun and just holding you hostage and just saying, "Don't cheat," And then the far other end is, PunkBuster, which is like, I'll kick you if someone sends you a funny message, but, otherwise just have fun, And Valve AntiCheat is a little somewhere in the middle, close to that second end, though, where it's mostly just trying to stop low-effort cheaters from, just buying some cheats and going to town. So some more stuff to look at, if you're interested in this kind of stuff. Handlemaster is used, it's only in Windows 7, I believe, but to perform direct kernel object manipulation by abusing a CPU Z driver. And if my memory serves me correctly, I'm pretty sure that Valorant's anti-cheat actually blocked you if you had those bogus drivers installed, because they were vulnerable enough to allow user land to start messing with memory. So, interesting stuff. You can get kicked out of a game because you haven't updated your drivers recently. That's how far you have to go, though, to really try to ensure integrity. And then the stuff like DSC fix with driver signature enforcement, I believe. Things to get around Windows demanding that all kernel modules and drivers be signed, which it has started demanding as of late, to try to improve security and make it harder to get rootkitted. And also, Mumble source code would be interesting, because Mumble has some kind of integrations into games where it can do like positional audio and that kind of thing. And it also needs to be able to do an overlay, which is more relevant here, actually. And so, overlaying stuff onto a game is quite a bit like doing wall hacks. I believe there have also been cases of people getting kicked from games because of, Discord overlays triggering an overly zealous anti-cheat. So it is really interesting how easily the line blurs and gets really fuzzy between, kind of above board programs and just cheating, as well as between preventing cheating and just malware. So that just about wraps up the talk for today, though. So next few weeks, we'll probably be talking about some more specifics of things like executable headers, because those are a kind of fun topic to look into, both on Windows and on Linux. But to keep on top of what we're doing next, I highly suggest joining us on Slack. If you go to our website, rpis.ec or rpisec, you will find a link to it there. So I do hope to see all of you there if you aren't already on the Slack. Thanks for coming by, and that wraps things up.